Okay, let's begin. Welcome to double slit hide and seek. This is a strange experiment I'll be describing today. So this is extraordinary concepts in physics, Physics X, being taught at Michigan Tech. I am Robert Nemeroff, professor here. So this is being taught for credit at Michigan Tech. It's trying to focus on concepts and not math. Anyone is welcome, especially to look at the videos, which are in several places. I understand they're on iTunes. No textbook is required, so all you need is your attention. You can find them on a place called Starship Asterisk, which is the discussion board for the astronomy picture of the day, and it's hard to read this, except if you see the slides, and this says /skylive.net/*view forum F is equal to 39. So you can find it on web there. And all the lectures are there. All right. So you can find this online. So I'll now start today's strange lecture. Something called the offshore experiment. So I'm going to build up to the offshore experiment with a simple start here. So as I like to do, I like to make this class experiment based. So let's say you have a classic double slit experiment, of which we've done many. We've discussed many in the past here. So a double slit experiment is performed at the location of, dark interference minima, they're recorded. Now wires are placed at these minima, and the image screen is now moved back. So you have your double slit here. You have your source of photons. Could be a laser. You have your double slit experiment here, and then you have an image screen. And on this image screen, you get an interference pattern. So we'll show it like that. So then what you do is you put wires here at the locations of the minimum and move your image screen back. So this is the slit screen. This is the image screen. And the question is, what pattern now appears on this image screen here? Is it an interference pattern? Does no interference pattern appear? Or does an image of Albert Einstein appear asking you to stop this foolishness? Okay, so go ahead and say it is an interference pattern. So the wires will have a little effect. They would have no effect if the flux of the interference minimum were really zero. I'll clear this so you can read that. This can't be, however, since the minima closer to one pinhole should receive a higher amplitude quantum wave than from the other pinhole. So, so my understanding of this experiment is not 100%. I know it's unpopular for professors, instructors to say that, so I'm giving my best bet. I'm not sure why this doesn't work with slits, but the offshore experiment is coined in terms of pinholes. So I've gone through this actually several times, trying to understand it. It's really interesting. I think I understand it pretty well to describe what happens. So here we go. That one was an easy one. So if you're priding yourself on getting that right, well, good job. You've seen probably some of the past lectures or know about the double slit experiment, but it's going to get stranger. Okay, next, well, here's what they're trying to do. Offshore and others have tried to come up with a double pinhole experiment that determines which pinhole path information for photons after they pass the wires placed at the interference minima. So the idea is that determining which path information should destroy the interference pattern. But what happens if you do this after the very existence of the interference pattern was established by the wires? So again, we have another pretender to this throne who's going to try to take the sword out of the stone. This set of experiments is going to try to find which slit information, which pinhole information the photons went through, and at the same time get an interference pattern. So you can say, oh, it was interference, but this photon went through that slit, and this photon went through that slit. So that's the idea. So the way they do this is they want to go through progressively more complicated experiments. So after that simple experiment, the double pinhole experiment is repeated, except now we will attempt to determine which pinhole information for the photons. For now, the opaque wires are removed. A lens is placed after the slits that would create an image of the pinhole screen on an image screen further out. Now, however, two mirrors are added so that the light from the north pinhole is directed only to the north image screen, while light going from the south pinhole is directed only to the south image screen. So the question is, what patterns are seen on the north and south screens? So you might be a little confused with the setup. So, so you have your normal double slit experiment. All right, let me just check. Well, so double slit experiment. Now you have a lens. Now, this lens is going to create an image on this screen here, which might be the two pinholes. But we'll back those out and say, oh, wait, we're going to get rid of that one too. We're going to put in two mirrors. You can do it this way, I guess. And you're going to put two screens here. So this is image screen 1. I'll call this image 1. This is image screen 2. This is a mirror, sometimes shown like that. And this is the slit screen. And this is the lens. So we made it more complicated. The idea here is that looking at these things, you might think that, here's photons come out of here, go through the double slits, that these image screens were now only going to show one slit. They're designed to show only one slit. So if they do that, what do you see? Do you see an interference patterns on image screen 1 and image screen 2, or do you not see interference patterns on image screen 1 and image screen 2? There's no wires in this yet. So the answer to this is, well, here's an experimental setup drawn. Let's clear out my crap. So here's photons coming in. Here are the pinholes. So somewhat collimated. Here's the lens I talked about. And then here are the mirrors. Actually, if you look closely, north is directed south and south is directed north, but it doesn't matter. You could flip the mirrors and have north go north. And so here are the two photon detectors, also the image screens right there. So this is a schematic taken from Wikipedia, which if you click here, you will be taken to the Wikipedia article for the Afshar experiment. And the answer is no interference patterns. Each detector sees only the image from its slit. So the north detector sees only the image from the north slit, while the south detector sees only the image of the south slit. Since there is no overlap, no interference is expected. This makes sense because which pinhole information is available? This can be seen when visualizing that only one photon at a time is released from the source. So now picture the source only releases one photon. Then if the north detector sees it, then it went through the north slit. If the south detector sees it, then it went through the south slit. So you can get which photon information for this. Now remember, the wires have been removed. So now comes the strange part. The double pinhole experiment is now repeated, but this time the wires that were placed at the interference minima are replaced. As before, a lens, so the rest of the experiment is the same. A lens is placed after the wires refocuses the light. Two mirrors are again put in there, so the north pinhole is directed to the north image screen, and south pinhole is directed to the south image screen. But now you put these wires back. These wires used to be at the interference minima. So what's going to happen? Are these wires suddenly going to see a no interference pattern and hence reflect stuff around? Or are they going to still be at the minima of the interference pattern that used to be there? The wires might not know what's happening further down the light path. Or do barcodes come up? And when scanned, these barcodes charge you $6.66. So here's this experimental setup. So everything is pretty much the same. Well, this is here they're playing with one slit on and off. So this, except the wires are put back. So you can stare at this for a while. And hopefully if you're confused now, it's okay. It takes a while. I went through this several times before I really got it. Just go through the slides again. Go to the website. Go to the Wikipedia website. Think about what's going on. So no interference patterns. So adding the wires does not cause the photons to revert back to the interference patterns. So just putting the wires back, you are seeing the north slit with the north screen, you're seeing the south slit with the south screen. Putting the wires back doesn't seem to change the interference pattern. So what's going on? How can the wires be at the minimum of the interference pattern, yet you don't see an interference pattern? How can that be? Well, here we go with the full Afshar experiment. Now we're going to measure flux. Not only we know if there's an interference pattern or not, now we're going to measure flux. So if the photons are not interfering, one would expect the wires to reflect and diffract a significant amount of source flux because they're sitting in the middle of brightness, not minimum of interference patterns. Therefore, the experiment is now repeated, except now the total flux of the image screen is measured. Do the wires significantly affect the flux measured by the detectors as they will scatter photons? Or do the wires not affect the flux measurement as they occur at flux minima of the now gone interference pattern? Which is it? So Afshar came up with a clever experiment. Do you see the flux that you would expect of the interference? Do you see the no interference flux? Or do left out details determine everything? So how does this double slit experiment work? Is there an interference pattern or not? Can you both get an interference pattern and determine which way the photons went? Which do you think it is here? Interference flux, no interference flux? This is a tough one, even for people highly schooled in quantum mechanics. It turns out this has been done. It is interference flux. The wires scatter very little light, as if they were at the minimum of the interference pattern. Yet the image screens show images of the slits, as if there were no interference patterns. Does this violate complementarity? The quoted, frequently cited effect that you can't essentially have both a particle and wave phenomena at the same time? Has this experiment shown interference pattern and which path information? Yes, no, or maybe so. So, the answer to that is Afshar and several others think that yes, they've now defeated complementarity. They can tell you both which way the photon went and that this photon participated in an interference pattern. Many others claim no. And the consensus also appears to be no, although oddly enough, even in the literature, recent literature, people are debating why the answer is no. So interpretations of the experiment are controversial and the debate becomes quite technical. One answer that I find somewhat satisfying is that the specific photons for which path information has been determined cannot themselves wholly create an interference pattern. And that's not seen here, so you have to think about that, to parse that phrase. So the photons that are going through for which you see the witch slit information, they're not the ones who are not bouncing off the wires. So in some strange sense, it might all make sense, but in a very weird quantum mechanical way. And so this might not be clear, but it is another limitation on the double slit experiment and just how weird it is. And with that, I will leave you with the occasional refrain. Please keep Schrodinger away from your cat.